Okay, grade 12, this is our flipped lesson on thermochemistry, standard heat of formation. If you haven't already, there is a fill in the blank note that goes right along with this PowerPoint and lesson, and it's on the website. It's called Standard Heat of Formation, fill in the blanks. You can go and print that out if you want. Enthalpy. Enthalpy is represented by the letter H. It is the heat content of a given substance. It is not measurable, but what we can measure is the change in enthalpy, and that's represented by delta H. The enthalpy of elements in their elemental state is taken to be 0. So basically how you see it on the periodic table, so sodium as Na, the only exceptions to this will be your diatomics, your O2, Cl2, and their elemental state. Enthalpy in the elemental state will be 0. What we know is that the heat of reaction is equal to the change in enthalpy of a reaction is the enthalpy of the products minus the enthalpy of the reactants. What we can see here is that if you have hydrogen gas plus chlorine gas to create hydrochloric liquid, hydrogen chloride as a liquid, what we have here are two things in their elemental state. So we create our reaction. This should be HCl. Create a reaction. Here's your products minus all of your reactants. But what we know is that this is equal to 0 and this is equal to 0. So really the heat of the reaction, the change in enthalpy, is equal to the heat of hydrogen chloride times 2 because you get 2 of them in the reaction. In the above reaction, what we see is that this is a formation reaction. We took two different things in their elemental state and we created a new molecule. If you write it like this, 1/2 H2 plus 1/2 Cl2 to give us HCl, we have 1 mole here. So our change in enthalpy of the reaction, 0, 0, is actually the same as our heat of formation of hydrogen chloride liquid. So what general statements we can make is that the heat content of elements in their elemental state is 0. So this is as you see them on the periodic table except for your diatomics. The heat content of a compound is their heat of formation. The heat of a reaction is equal to the heat of a reaction equals the heat of the products minus the heat of the reactants. Let's change that. Last but not least, the big one is that the heat of a reaction is equal to the sum of the heat of the formation of the products minus the heat of the sum of the formation of the reactants. And this guy here, that symbol means sum of. So let's practice writing out how you would determine the heat of a reaction if you're given something like this. So what we know is that the heat of reaction is equal to the heat of the products minus the heat of the reactants. Get rid of that F for now. We know that the heat of the products is equal to the heat of formation of the products minus the heat of formation of the reactants. So we write it as the sum of the heat of formation of the products minus the sum of the heat of formation of the reactants. So we look up here, we check to see if anything's in its elemental state. Nope, 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 nope. So then, in brackets, now we're looking at our products. So heat of formation of NaCl plus the heat of formation of H2O, and we should have a state here because it does matter, but we don't, minus the heat of formation of your reactants. So heat of formation of HCl plus the heat of formation of sodium hydroxide. And if we have values for these, we can plug them in and solve. Different ways of determining delta HR, calorimetry, we've done standard heat of formation, we're doing total bond energy, and Hess's law. I don't know if it'll be tomorrow. Standard heats of formation. If you would like another quick video on how to do that, you can click on that on your worksheet if you still have it open on the computer. The standard heats of formation are the change in enthalpy or heat associated with the formation of 1 mole of a substance at 1 atmospheric pressure and 25 degrees Celsius. These are standard values that you can get off of a chart, and you will be given them. What we need to remember here, things we need to remember here is that you must account for the number of moles that you have, and you must account for the physical state that they're in, because the heats of formation, for example, for water in a gas, liquid, solid, or aqueous, well, water will be in an aqueous state, but gas, liquid, and solid are different heats of formation depending on the state that it is in. Standard heats of formation will be given. Standard heats of formation in the elemental state are 0. Don't forget your diatomics. We're going to quickly watch a bit of a video. I want you to copy down the example as we go on, and then we will try an example of our own.
In this example equation. So there's a way to use the standard heats of formation for NO, O2, and NO2 to find the overall standard heat of reaction for this reaction. And that looks like this. The standard heat of reaction is equal to the standard heats of formation of all the products minus the standard heats of formation of all the reactants. So I'm going to need to know the standard heats of formation for all the reactants in the products. And that information can usually be found in a table of thermochemical information, such as this one. So we're going to use the values in this table to help us figure out the overall delta H, the overall heat of reaction for this reaction. Let's start by getting the values for each of these compounds from the table. The first reactant, NO gas, has a standard heat of formation of 90.37 kilojoules. I'm going to multiply that by 2 because there are 2 NO molecules on the reactant side. Next, I'm going to look at oxygen. Now, oxygen is an element in its most stable state, and any element in its stable state at the standard condition is going to be 0. So oxygen is just a 0. Next, I'm going to look up NO2, which has a standard heat of formation of 33.85 kilojoules. And I'm also going to multiply this by 2 because I have 2 of them. So the total for the nitrogen monoxide gas is going to be 180.74 kilojoules. Oxygen is still 0. And the total for the NO2 gas is going to be 67.7 kilojoules. So now I'm going to use this equation and this information to find out the overall heat of reaction for this reaction. So the standard heat of reaction is equal to the total heats of formation for the products, which is, in this case, only 67.7, minus the total heats of formation for all the reactants, which in this case is going to be 180.74. If I now solve that, I'll see that the overall standard heat of reaction is negative 113.04 kilojoules. And that's how I can use the standard heats of formation for all the compounds in the equation to find the overall heat of reaction.
Okay, we're going to finish off doing an example. All right, here's the example. Copy that down. Some things that we need to know for this is that your heat of formation of CO2 is equal to 393.5 kilojoules per mole. Your heat of formation of liquid water why do I have water there? All right, let's try another example. This time we're reacting hexane with oxygen to get carbon dioxide and water. We want the heat of reaction using standard heats of formation, so you need the standard heats of formation. Standard heat of formation of hexane, that's your C6H14, is equal to 95 kilojoules per mole. Oxygen is in its elemental state here, so it's 0. Standard heat of formation of carbon dioxide is 393.5 kilojoules per mole. And the standard heat of formation of water in its gas, this should be liquid state, is equal to 285.9 kilojoules per mole. All right, so if you would like to pause it right now to try the equation on your own, go ahead. All right. Heat of reaction is equal to the sum of your heat of formation of your products minus the heat of formation of your reactants. So our products, we've got carbon dioxide, we have 12 of them. This is per mole, this value here is per mole, so we have to times it by the number of moles we have. 12 times 393.5, don't forget your negative sign. Put a bracket all around that, plus we've got to do the heat of formation of water, so 14 times this negative value, 285.9, minus our products, we only have one because oxygen is an elemental state, 2 times 95. So we've got 12 times negative 393.5 plus 14 times negative 285.9, which gives us minus 8,724.6. Subtract. And our final value is 8,534.6 kilojoules for this heat of reaction. Negative sign tells us that it is what kind of reaction? Exothermic. If you feel like you can get going on the questions that you've got, go right ahead. Otherwise, we will see you in class for another example tomorrow.